Welcome to the course on network theory. Today's topic is going to be independent and dependent sources. So the references which have been used, Ravi Singh, which is network analysis and synthesis, and William Haid, electrical circuit analysis. These two textbooks have been mainly used as references. The contents which we are going to be discussing is on independent sources, dependent sources, and basically ideal and practical voltage and current sources. Now, what are independent sources? When we're speaking about sources, the first thing is voltage source. So, ideal and practical voltage source, what is the difference? An ideal voltage source has a constant voltage across its terminals. So, this is normally the independent sources are represented by a circle symbol, and a voltage source has a polarity which is shown. So, this is the representation of an ideal voltage source. So basically the ideal voltage source is supposed to have a constant voltage at the load terminals. So here the terminal voltage will be equal to Vs only. Whereas there is in the practical voltage source, the practical voltage source is going to be represented with a series internal resistance like this. So with the addition of the circle symbol and the polarity, this is your source, it has got also an additional internal resistance in the representation. So when we are speaking about the ideal sources, ideal voltage source, like I said, this is the representation of an ideal voltage source, and these are the load terminals. So here what happens is that there's no internal resistance, because of which the load, if you're connecting a load over here at this terminals, the load voltage VAB is going to be equal to Vs only. Or we can say, if we are plotting the load voltage versus time or versus current maybe, we can say that it is constant. This is how your representation of the graph is going to be looking like. Whereas in the case of a practical voltage source, it has got an internal resistance. So this is your practical voltage source, and there is this internal resistance with this. Now what will happen when you are connecting a load? So these are the load terminals. So as soon as you connect a load over here at the load terminals, what is going to happen? Current is going to flow, and VAB, which is your load voltage, which is going to be Vs minus I into Rs, which means that as Rs increases, your load voltage is going to decrease. So if you're plotting it, we'll get a voltage like this. This will be your ideal case when your current is 0. As the current increases, the voltage is going to drop. So it basically depends upon the load also. As the load current increases, your load voltage is going to drop. Also at the same time, we can also see that it depends upon the series resistance also. So as low the resistance is, the lesser the drop over here. So normal practical voltage sources are always designed to have a very small internal resistance. An ideal voltage source will have Rs is equal to 0, and practical voltages have some internal Rs, but resistance Rs should be designed as small as possible. So these are about voltage sources. At the same time, when we are speaking about current sources, so ideal current source, now the current source is again, these are the independent sources. So they are going to be represented by a circular symbol with an arrow. This could be upwards or downwards. Now, this is the representation of the current source, and these are the load terminals. So if you are connecting a load over here, then IS is equal to IL. So when you're connecting the load, the IS and IL are going to be the same. Now, whereas when we have ideal, so which means that ideal source has a internal resistance which is equal to infinity. When we are speaking about the practical source, obviously, then comes a resistance. So practically, all sources have some resistance, but these resistance are represented in parallel to it. So these are the load terminals. So you can see that the load current will depend upon the value of the parallel resistance which is connected over here. So speaking about the ideal or practical current sources, as we said before, ideal current source has got an internal resistance of infinity. So here Rp is infinity, whereas a practical current source is shown with a parallel resistance. So parallel resistance Rp is also, or RSH, that is a shunt we call it as. This value of this depends, the value of this actually decides how much current will flow into the load terminals. So what we can say is that since an ideal current source does not have any internal resistance, your load current versus time or versus voltage, if you say, this is going to be constant. So IL is going to be equal to IS, because there is no internal resistance is infinity here. The whole current is going, or it is like an open circuit over here. The whole current is going to flow to the load terminals. Whereas in this case, if you plot it, you have, this is the ideal current which should have been, that is the maximum current should, the IL should have been ideally equal to IS, but depending upon the value of your shunt resistance, the source current, this is your source current, some of it splits into the parallel resistance, and the remaining part goes to the load side. So the load current will depend upon the value of this resistance. So if a smaller value of Rp means that a larger current would flow through it and lesser current through the load, or if Rp is made as high as possible, then what happens? Smaller current would flow through this and larger current would flow through the load terminals. So when you show the representation of a practical current source, this is how it is going to be. Slightly the load current is going. So this is your load current. This is the ideal current case where Rp is infinity, and this is depending upon the value of your Rp. So depending upon the value of your resistance, the load current is going to be changing. So the shunt resistance should be made as high as possible. That is how the design is done. Sources. Now, when we are speaking about dependent sources, what are dependent sources? These sources, as the name says, depend upon some other quantity. Now, the sources are of two types, voltage or current source. Now, voltage or current source depending upon some other voltage or current. So you can call it as dependent or current control current source. Normally represented by the diamond symbol, and the controlling variable can be voltage or current. So normally what we have is, we can have four different types of sources depending upon how they are, on what parameter they are depending upon. So you can have a voltage source which depends upon another voltage. So it is a voltage controlled voltage source, like this first case. Or you can have a current source which depends upon a voltage. So again, it is called as a VCC, as a voltage controlled current source. Again, you can have the next type, which is a voltage source which is controlled by current. So current controlled voltage source, and the last one will be a current controlled current source. So here, hence we have got four different types. So two are voltage sources and two are current sources. So the voltage sources, one can depend upon voltage, the other depends upon current. Similarly, current sources, two types. One depends upon voltage, the other depends upon current. So when we are speaking about the voltage controlled voltage source, now this is the representation of a voltage controlled voltage source. Now, like I said, all these are dependent sources. So this is a dependent source because it depends upon a voltage. Now, dependent sources are represented by the diamond symbol. So this is how, and since it's a voltage, it will be shown with the polarity. So now what we have is, this is the black box which represents the output voltage, which represents the circuit. So now the source, the output voltage is a dependent source. So the output voltage is dependent upon some voltage somewhere in the circuit. So which means that the output voltage, you are going to be representing it as the terminals. Output terminals are represented as CD. The input terminals are represented as AB. So VCD, that the output voltage is proportional to another voltage, or in other words, if you write it, the proportionality constant can be represented as mu. So the output voltage VCD is represented as, it is equal to mu into VAB. This is how it is represented. So this is the voltage controlled voltage source. Diamond symbol for the dependent source. Since it's a voltage, it is shown with a polarity, and the output voltage depends upon an input voltage. So it is represented as mu into VAB. So you can see that mu is equal to VCD divided by VAB. So it's a voltage divided by voltage. So it's a dimensionless constant, or it is also called as a voltage gain. So it is dimensionless. An example of this is an output voltage of an op-amp. So an op-amp is an amplifier, operational amplifier, which you have got some components to it. There will be some resistances like this, and there can be something like this, and you have the input voltage and the input. There are two terminals for the op-amp. This is called as a differential amplifier. The output voltage depends upon the difference between the voltages at the input terminals. So output dependent upon an input, so it is a voltage controlled voltage source, right? Okay. Now, speaking about the voltage control current source, the voltage control current source can be represented by, again, since it's a dependent source, the diamond symbol with an arrow for the current source. So the output current, now ICD, it is the output terminals are CD and the input terminals again AB. So ICD is proportional to the input voltage, which is VAB, which means ICD is equal to, now, the proportionality constant is going to be equal to current by voltage. So, it is a conductance, or it is called as a transconductance. So, the transconductance GM is equal to current, output current by input voltage. Since it's a conductance, its unit is in Siemens. So, example of a voltage controlled current source is an FET, or a field effect transistor. So, field effect transistor has got three terminals, a gate, drain and the source. The input voltage, or the VGS, controls the output current. So FET is an example of a voltage controlled current source. Similarly, we have the current control voltage source. Now the current control voltage source, again in similar ways, you have the output VCD is proportional to the input current IAB. So VCD is proportional to the input current. So the output voltage. So again you can see that the representation is with a diamond symbol and polarity, since it's an output is voltage. The output is depending upon a current. So the proportionality constant is going to be voltage divided by current, which is a resistance. So this is your trans resistance. Since it's voltage divided by current, its unit is ohms, and the examples are that of a voltage shunt feedback amplifier using transistor. Not going into the circuits of this, but basically we can understand that a current control. So here the current control voltage source has the output voltage controlled by the input current. So current control current source, similarly, current control current source is something which has got output current dependent upon the input current. So output current divided by input current is defined as a dimensionless. So current by current, a dimensionless quantity, which is equal to beta. So basically we have in this case, ICD is proportional to IAB, and the proportionality constant is equal to beta into IAB. So beta is ICD divided by IAB, and it is dimensionless, right? An example of this is that of a BJT. Again, BJT is a bipolar junction transistor which has got the output current as a collector current, which depends upon the input current, which is a base current. So IC can be written as beta into IB. So similar to the FET, which was a voltage controlled current source, this is a current controlled current source. The BJT is a current controlled current source. So these are examples. These are actually called as dependent sources. Now, where do we use these? So the application of dependent sources are basically in modeling. Whereas when sometimes we need to use transistors, so you can have a BJT. This is the symbol of a BJT, or you could have MOSFET. This is something, this is a MOSFET, right? Or you could have an FET. So basically, wherever these there are circuits like this, complex circuits involving transistors, the transistors can be modeled in the form of current sources. For example, a BJT can be modeled as a current controlled current source. The MOSFET could be modeled as a voltage controlled current source, and so on. So different devices can be represented by these dependent sources, and these dependent sources and these are basically used to analyze a circuit to find out different parameters. So in modeling different devices, these dependent sources are used. So we'll see in the next video how we work with independent and dependent sources to simplify circuits. Okay, thank you. We'll see in the next video.